Machine learning applications have been the target of considerable normative scrutiny over the past decade, including at this very conference. But people are increasingly concerned about machine learning research too. Members of the research community have begun to ask how they should take ethical considerations into account when developing research agendas, conducting research, evaluating research contributions, handling the publication and dissemination of their findings, and so on. The community has experimented with a variety of recent proposals for dealing with some of these issues, including ethics codes, ethics boards, ethics and impact statements, ethics review in peer review, and funding applications. While the community's attempt to grapple with these issues has been encouraging, there remains a good deal of confusion about the range of ethical issues at stake, the roles and responsibilities of different members of the research community, and the mechanisms that are best suited to address these issues. In this work, we try to bring some structure to the debate by clarifying the range of relevant ethical issues at stake and distinguishing them from each other. In particular, we identify three distinct clusters of concerns. First, research integrity, which concerns reliable scientific findings. Second, research process harms, which concerns the risks posed to a range of stakeholders due to the design and execution of a research project. And finally, downstream consequences, which considers the potential impacts resulting from applications of the research findings. We then consider the range of actors and governance mechanisms that might help to address the ethical issues in each of these categories, emphasising when different actors or mechanisms are better suited to the task. We believe such clarity is needed for a number of reasons. Firstly, determining what ethical responsibilities people might bear requires first understanding the ethical issues at stake. Some of the disagreement in the community is due to confusion, not fundamental differences in belief. Secondly, buy-in and compliance requires that people understand the ethical issues at stake and recognise the value of addressing them. It's also difficult to evaluate the efficacy of interventions unless there's clarity about their goals. And finally, some ethical issues may be in tension. We might not strike the right balance if we don't understand the issues and trade-offs. For example, ensuring the privacy of research subjects may enable research that produces findings that can be used to violate others' privacy. The first category we have identified is research integrity. Research integrity focuses on practices that ensure robust scientific findings. This encompasses a wide range of practices which we've broken down into three subcategories: fraud and misrepresentation, reproducibility and replicability, and assumptions and limitations. Fraud and misrepresentation includes issues such as fabricating data, falsifying results, for example p-hacking, misrepresentation of findings such as conflating exploratory and confirmatory analysis, which is often unintentional, and potentially cherry-picking examples. Failing to report negative results, conflicts of interests, especially when researchers may feel pressured or incentivized to reach conclusions favourable to those funding the work. Reproducibility is generally considered to mean providing the necessary information so that others can rerun the experiment, whereas findings are considered replicable if new studies arrive at the same results. Techniques for reproducibility include sharing data, code, and other artifacts, and could potentially involve, especially in the case of machine learning research, reporting details such as compute requirements or specialised hardware used. This helps other researchers determine what resources they need to reproduce the experiment. Replicability can involve using appropriate analysis techniques, making statistically sound performance claims, accurately representing the evidence supporting a claim, and ensuring soundness of proofs. The third subcategory involves appropriate disclosure of assumptions and limitations. For example, the assumptions about the data, method, and context of use, or limitations that potentially affect the validity and generalizability of the finding. It may also involve quantifying uncertainties. Failing to do this can skew research directions, distort conclusions, and potentially result in the systems being applied in inappropriate settings. The second category we identified involves harms that might result from the research process itself. We identify four main subcategories. The first is ethical obligations to research subjects, which includes individuals participating in the research study and those whose data is used within the research process. This is the traditional domain of so-called research ethics, and where institutional review boards play a crucial part in regulating research conduct. In the United States, research involving human subjects is expected to abide by the principles of respect for persons, operationalized as informed consent, beneficence, operationalized as minimizing risk and maximizing likely benefits, and justice, operationalized as an equal distribution of risks and benefits. Research that does not involve human subjects falls outside its scope. Second, we have the ethical treatment of workers who contribute to the research. This covers, for example, the compensation and working conditions of researchers and crowd workers. This could even include the psychological harms inflicted on those exposed to particularly upsetting content as part of the dataset creation. Next is a consideration of research process impacts to non-participants. For example, road users who may be impacted by the testing of autonomous vehicles despite never volunteering to be in the study, or those who may be harmed if accidents in weapons research affect the nearby area, or if malware escapes the lab. It also covers the potential environmental impacts of training resource-intensive large models. In all these cases, the affected parties are not directly involved in the research process and have not consented to bear such risks, yet they may experience significant harm. Finally is the appropriate management and use of assets, including data, code, and models. Researchers must ensure, and often demonstrate, their right to use these assets. Increasingly, this involves compliance with appropriate privacy or data protection laws such as GDPR. The third major category we identified was the consideration of the potential downstream consequences of the research. This can include both the impacts that result from applications that work as intended, as well as those that result from errors, accidents, or misuse and abuse. It comprises three aspects. Firstly, the consideration of research questions and problem formulation. This may involve choosing research questions and directions with future impacts in mind, and in some cases potentially not pursuing certain avenues if the risks outweigh the benefits. Secondly, we have the ongoing consideration of downstream impacts throughout the research process. This could involve finding methods to evaluate not just accuracy, but also societal impact, fairness metrics, for example. It could also involve reflecting on possible downstream consequences and the extent to which the research enables dual-use technologies, or could be exploited by malicious users. Disclosing potential risks and appropriate uses of the technology may play a role here. Finally, there is the question of how to actively mitigate the risk of any negative downstream consequences that have been identified. As those closest to the research, researchers may sometimes be well positioned to both identify and implement mitigations. Other approaches include technical interventions, organizational procedures, or governance strategies. Coordinated disclosure, a mechanism used in computer security to handle discoveries of vulnerabilities, could serve as a model for sensitive machine learning research. Some companies have adopted a staged release approach to their research to minimize the risks of malicious users or unanticipated consequences. Having categorized the different components of ethical research, we then examine the different governance mechanisms that are or could be used to foster ethical research practices. Additionally, we suggest which stakeholders or parts of the ecosystem may be best placed to execute these mechanisms. Mechanisms can be broadly grouped into the following categories: agenda setting, i.e. helping direct the research towards socially beneficial outcomes; training, to ensure researchers are equipped to adhere to best practices; rules and requirements, i.e. formal obligations that aim to mitigate risks; review, including peer review and institutional review; incentive mechanisms to encourage responsible research practices; complaint mechanisms to ensure there are processes for complaints and protections for whistleblowers; sanctions, either informal reputational penalties or more formal restrictions in egregious cases. And stakeholders include research institutions, publication venues, legislators and regulators, funders, educational institutions, and professional societies. Here, we can see examples of the mechanisms that can address issues related to research integrity. Taking reproducibility and replicability as an example, we might see research institutions engage in training to ensure researchers are equipped to perform appropriate analyses and are aware of the pitfalls of statistical manipulation. Publication venues often have requirements and checklists around making data and code available and disclosing key details such as compute spending to aid reproducibility. Publication venues and funders may expect pre-registration of studies, and funders could also invest more in scientific reproduction projects, in particular for research that would be prohibitively expensive for non-industry researchers. Here we are looking at the mechanisms to mitigate research process harms. Taking the consideration of research process impacts to non-participants as an example, we might see research institutions expand ethics review boards and IRBs to consider a wider range of externalities. They may additionally impose safety standards and provide processes and protection for whistleblowers. Publication venues might require disclosure of environmental impact. Funders or professional societies might provide resources and tools such as emissions calculators. Here we can see example mechanisms for addressing the issue of downstream consequences. Taking the ongoing consideration of impacts as an example, some publication venues have already experimented with ethics and broader impact statements to encourage researchers to reflect on the impacts of their work. Model cards are emerging as a popular approach for disclosing appropriate use of models. Research institutions and funders may have a role to play in promoting beneficial research projects and establishing ways to measure downstream impacts such as fairness or privacy metrics. See the paper for a breakdown of governance mechanisms organised by the stakeholder in a position to intervene. The three main categories we lay out in this paper represent how thinking about scientific conduct has developed over time. Research integrity aims to support the rigour of the scientific method with roots going back centuries. The rights of human subjects in research can be traced back to the 1948 Nuremberg Code and 1979 Bellman Principles. Recently, there has been increasing attention on societal impacts. In our paper, we identify a number of areas where the field of machine learning has room for improvement across these categories. In terms of research integrity, machine learning often suffers from problems with replicability. The field does not have a strong tradition of RCTs. Instead, it tends to use benchmarks and risks overfitting. Additionally, a common critique of novel results is that they've been cherry-picked to demonstrate the system in the best possible light, or that claims have been overstated. Moreover, external verification of these findings is made difficult due to, for example, large compute requirements which inhibit reproducibility. The field of machine learning in particular struggles with conflicts of interest, given the influence and funding of research from large tech companies. Some have questioned whether simply disclosing this is enough. In terms of mitigating research process harms, there are some kinds of research that in the United States would fall under IRB regulation. However, it's only recently that welfare considerations have been extended to data subjects, and there are other stakeholders that are not usually considered, such as data workers. Given the fast-paced nature of machine learning research and the quickly evolving nature of working with data, data regulation requires ongoing development, for example, policies that cover the use of problematic or biased datasets. An additional externality of machine learning research is the environment. Training large models can be incredibly resource-intensive. It's possible that compute requirements and environmental costs should be included in the process of considering research process harms. In terms of downstream consequences, there have been a number of attempts to build consideration of societal impacts into the machine learning research process, such as the NeurITS Broader Impact Statement and paper checklist. However, ethics statements are not widely adopted, and more work is needed to best determine how they should operate and to assess their effectiveness. For example, how they should apply to very theoretical research versus research with more potential for deployment, and how to account for research that provides incremental advances versus significant breakthroughs. Additionally, we should consider how to avoid placing a disproportionate burden on researchers to compensate for insufficient governance mechanisms elsewhere. Thank you for watching. By providing this framework, we hope to enable more effective conversations around how machine learning research can be conducted ethically and with positive social impact.